we're going to talk about line integrals through vector fields. And I guess if there was a real life example of this, I'd like you to keep in mind as we proceed through the problem, and it is maybe walking outside on a really windy day. And you notice that sometimes the wind is blowing in your face, and other times it's blowing from the side of you, and then sometimes from behind you. Kind of like the wind behind us, it gives us a little bit of push because there's some help. And then other times we don't get so lucky, the wind is directly in our faces. Okay, so let's just consider a two-dimensional example for a second. This translates very nicely using vectors into the 3D world, so we'll just keep things simple. So let's say you decide that you're going to walk through space. You're going to follow this path, right? Maybe this corresponds to t equals a, the beginning of your trip, and this is corresponding to t equals b, where your trip ends, and you're going to move in this general direction. Okay, so as you walk through this vector field, at any given point, we can stop you and say, hey, where are you heading at this instant in time? And that would be well represented by what we're going to call t, which is the unit tangent vector. So the unit tangent vector. Now, as I get at this particular point, I don't know what I'm going to call it. I'm going to say this is t equals t star, some special value of t. At that particular point in time, it's also true that the wind might be blowing on you. So maybe, just maybe, at this point, the wind is doing something like this. And I'm going to call that f of t star. In other words, the amount of force we're experiencing at that particular location. Now you'll notice that blue vector I just drew is not in the direction of the green tangent vector, but it does have a component that is in the direction of the green tangent vector. So what we could do is we can find the shadow that vector f makes on the unit tangent vector by dropping a perpendicular. And then this yellow vector here I'm drawing in, it's hard to see there, but that yellow vector is the amount of help I'm getting from the vector field. That's the component of the blue vector f that's blowing in the same direction as my unit tangent vector. Okay, so this story happens all along. At any point along the graph, I can sort of ask them to talk about the same things. So, for example, if it went out here maybe to this point, it would be a green tangent vector, a unit tangent vector again, t. And maybe the force vector there is acting differently. So maybe it's blowing something like this. And when I find the shadow back onto t, then the little yellow vector this time is a little bit shorter. I'm not getting as much help at that point. It could even be the case that vector f blows in the wrong direction and is blowing against me. Okay, so there we are. Now, before we can go any further and build what's known as a line integral through a vector field, I need you to recall a special fact about dot products. So you have two vectors a and b. A dot b can be found by finding the norm of a times the norm of b times the cosine of the angle between them. And the geometric interpretation of this is what's so important. So let's take a look at, for example, let's call this vector A. Let's call this vector B. And suppose I'm interested in finding the shadow that vector A makes onto B. Just kind of almost in the same way we were just doing in our picture, right? We're finding the shadow that the force vector leaves on our unit tangent vector. And so say I want this distance, I want this amount here. Well, if we know the angle between the vectors, we can just find the length of A. The length of A is denoted norm A. This whole thing has length norm B. But I really want to know what x is. So I could just do a little bit of basic trig, right? So we can say cosine of theta equals adjacent x over the length of A. or norm A cosine theta is equal to x. Well, if we look at this dot product up here, we can underline norm A and underline cosine theta, and then just get rid of this rad B. We're going to divide that over this, not rad B, length of B, norm B. And what we end up getting is the length of A times the cosine of theta is equal to A dot B over the norm of B. So that's a pretty amazing fact. What this is actually saying is that if we compute this quantity, we take the dot product of the vectors and divide by the length, then we're getting the shadow that vector A makes on vector B. So let me say that again. This is the shadow that vector A makes on vector B. It's right here. It's this drawing in the picture, this purple vector, right? This is the length of that shadow is what that is. So the length is not actually the vector, it's just the length of the vector. And we can get it by just finding this. So it turns out that that's, if we go back to the picture here, we can do the same thing. If we want to find these little yellow vectors, then what we can do is we can say, well, the shadow of, we could say we really want, well, this is what we can say. We want norm F cosine theta, right? Just like this expression up here, norm A cosine theta. That would be the shadow that vector A makes onto vector B. And I want norm F cosine theta. But according to this definition, I could just do the vectors dotted divided by the length of the vector I'm finding the shadow onto. So this thing would be vector F dot vector T over the length of T. But don't forget, T is a unit vector, and that means it has length 1. So this just becomes F dot T. And now you're ready. You realize we could find F dot T at every one of these little points. This expression is the length of all the yellow vectors. And it would probably have T's in it stuff because you would get different values along the way. So that's it. Now you're ready to build your line integral. Really what you want to do is at every point you want to find those little yellow vectors along the curve and add them up. So how do you do that? Well, remember, we start at time A, we end at time B. So it's going to be an integral from A to B of F dot T, which is one of the little yellow vectors, and I have to multiply it by ds, which is small change in displacement. And this thing is called the line integral through a vector field. Now, it turns out that if you want to compute it, there's a more convenient way that you can do that. So keep in mind that vector fields, we haven't seen any examples of those yet, but a vector field might look like this. F of x comma y equals maybe x squared y times I plus rad y times j. You'll notice that this expression I'm writing has x's and y's in it. And this looks like we're just integrating, we have one little integral sign here. So we must be doing something clever. And what we're going to do is we're going to plug in a parameterized curve. This curve you're traveling on, this red curve, which I'm going to call C, we've already experimented with writing these things in parametric form. So that means we're going to convert this all to a function of t. So how am I going to write this? I'm going to write it like this. I'm going to say integral a to b f of r of t. And that just means we're going to take our expression for the curve, and we're going to sub it into the function. And then we're going to dot it with the unit tangent vector, which you can think of this way. You get a tangent vector by taking the derivative of your curve. You make it a unit length vector by multiplying, or I should say multiplying by 1 over its length or dividing by its length. So that's the unit tangent vector. And then finally, ds we've seen before. Ds we've written the following way. So I'm going to just respect the way you've seen it already. dx dt squared plus dy dt squared dt. Okay, but if you look at this thing, that's really just the derivative of your path, and we're finding the length of it, because that's what this square root of the square of the sum of the components does. It's Pythagorean theorem. So then you get this very pretty way to compute the line integral, because these two things really cancel. So when everything's said and done, you just get the integral from a to b of f of r of t dot r prime of t dt. And it turns out this is probably the most common way that we go about evaluating line integrals. So it's going to be a good place to stop. There's going to be another video to follow up where we practice computing the value of a line integral. Thanks for watching.